Hello, everyone. Imagine for a moment you're in the middle of the ocean. Not a lake, not a bay you can see across, but the true ocean. A vast, churning, infinite expanse of deep blue, indistinguishable in every direction. There's no land in sight, no landmarks. The sky above is a seamless dome. Your phone is dead. The GPS is broken. The compass is gone. All you have is your own two eyes. Your wits. You are utterly, hopelessly lost. For most of us, this scenario is the stuff of nightmares. We are a species tethered to technology, guided by satellites orbiting invisibly above our heads. To be without that connection is to be blind. And yet, for thousands of years, our ancestors did this routinely. They set out into that same blue desert, not in fear, but with purpose. They crossed oceans that would take. They did it without GPS, without radio, without even the maps we would consider essential. It seems impossible, like a legend or a myth. We think of them as primitives, clinging to coastlines, getting lucky. But what if that's completely wrong? What if their minds held a technology far more sophisticated than we can imagine? What if they possessed a form of genius so profound, so connected to the natural world? This is not a story about old, dusty tools. This is the story of the software that ran inside the human mind, the ancient code that allowed us to conquer the planet. The story begins, as so many do, in the cradle of civilization, the Mediterranean. This was the world's first great maritime highway. The Egyptians, the Minoans, the Greeks, the Phoenicians, they were the pioneers. At first, it was simple. You sail out of your harbor, turn left, and keep the land in sight. You navigate by recognizing unique features: a distinctively shaped cliff, a river mouth, a distant mountain peak. It is connecting the dots on a landscape you can see. But this has its limits. It is slow, it is inefficient, and it keeps you chained to the shore. The first sailors to break those chains were likely the Phoenicians. These master traders from the coast of modern-day Lebanon needed to get their goods, their precious cedar wood, their glass, their iconic purple dye, to markets faster and more directly than their rivals. Hugging the coast was safe, but it was for amateurs. The real money, the real power, lay in cutting straight across the open water. To do that, they had to look up. They had to read the sky. The sun was at its highest point in the sky in the northern hemisphere. It marks due south. Simple, by observing the sun's arc, a sailor could get a rough sense of direction. But the sun is a moving target. What you need is something fixed, something eternal, and for that you must wait for night. As the sun bleeds away and the sky deepens to indigo, the celestial map unfolds, and on that map, for anyone sailing the Mediterranean, it's not the brightest star in the sky, not by a long shot, but it has a unique property, a kind of celestial magic. Due to the Earth's axial tilt, as our planet spins, all the other stars appear to wheel and circle through the heavens. But Polaris sits almost directly above the North Pole. It is the anchor point, the linchpin of the entire night sky. It does not move. For an ancient, no matter where you were, no matter how the waves tossed your ship, you could find that star. You could find north. And if you can find north, you can find all the other directions. You are no longer lost. Suddenly, the sea was not a featureless void. It was a grid. The Phoenicians used this knowledge to build a trading empire that spanned the Mediterranean. The Greeks followed, using the stars to colonize distant shores from Italy. The goddess Calypso instructs Odysseus to keep the constellation of the Bear, what we call the Big Dipper, on his left as he sails. Why? Because the Big Dipper endlessly circles Polaris, acting as a giant cosmic arrow pointing the way. These sailors memorized the star patterns, the stories written in the sky. They knew which constellations were visible in which seasons. They built a mental clock, and a mental... It was a staggering intellectual achievement, but it had a fatal flaw too. In fact, what happens when the gods of the weather turn against you? When the sky, your only map, is stolen from you by a thick, impenetrable blanket of clouds, for days, for weeks. Suddenly your celestial clock is useless. Your divine compass is gone. You are blind again, at the mercy of the winds and currents, praying for a single break. And there is another, even more fundamental problem. What happens when you sail south? Far south, if you cross the equator, Polaris, your faithful guide, sinks below the northern horizon and vanishes. The entire map of the northern sky is gone, replaced by a strange and unfamiliar set of constellations. The anchor is gone. You are in a new world, under a new sky, and the old rules no longer apply. But for the next great wave of explorers, the ones who would venture into the truly monstrous oceans, these were not theoretical problems. They were matters of life and death, and their solutions would require a new kind of genius. Our story shifts north, to the cold, grey, violent waters of the North Atlantic, to the land of fjords, ice, and sagas, the Vikings. When we picture Vikings, we think of bearded warriors in horned helmets, which they didn't wear, by the way, leaping from longships to raid coastal monasteries, and they certainly did that. But that's only half the story. The Vikings were, first and foremost, the most audacious and skilled sailors of their age. Look at a map from their Scandinavian homeland. They didn't just raid England and France, they sailed west. They colonized the Faroe Islands. They settled Iceland. They established a colony in Greenland that lasted for 500 years, and from there they made it all the way to North America. 5 centuries before Columbus. They did this in open-decked longships, magnificent vessels, but terrifyingly exposed to the elements, and they did it in one of the most notoriously difficult sailing environments. The North Atlantic is famous for its storms, its fog, its endless weeks of oppressive, grey cloud cover. Polaris was often hidden. The sun was a pale, watery disk, if it was visible at all. How did they do it? How did they navigate hundreds of miles of open, featureless, storm-tossed ocean to find a place like Iceland? For centuries, historians assumed it was mostly luck, combined with an uncanny knowledge of seabirds and whale migration patterns, and those things were certainly part of it. But the Norse sagas, their epic poems and histories, spoke of something else. A tool, a magical artifact. They called it the Sphelarstein, the sunstone. For a long time, scholars dismissed this as pure fantasy. The saga of King Olaf, for instance, describes a scene where the king, to test a man's skill, asks him to determine the sun's position on a completely overcast, snowy day. The king grabbed the sunstone, held it up, and saw where the light radiated from the stone, thus pinpointing the hidden sun. Magic. Right? A fairy tale, except maybe it wasn't in 1967. A Danish... What if the sunstone was real? What if it was a specific type of crystal with a peculiar property known as birefringence? Crystals like calcite, tourmaline, or cordiorite, all of which were available in Scandinavia, have this property. They split light into 2 rays. If you look through one of these crystals and rotate it, the brightness of the 2 images changes. Ramsco realized that these crystals react to... But when it passes through the atmosphere, it scatters and becomes polarized. The pattern of this polarization is directly related to the position of the sun. Even on a completely overcast day, or when the sun is just below the horizon at twilight, enough polarized light gets through for these crystals to detect it. By holding up a crystal like cordiorite and rotating it until the 2 rays of light passing through it were of equal brightness, it wasn't magic, it was physics. The theory remained just a theory for decades, a tantalizing possibility. But then, archaeologists began to find evidence. A crystal of Iceland spar, a type of calcite, was found in the wreck of an Elizabethan ship that sank in 1592. Long after the age of Vikings, but still suggesting such tools were in use. It was found right next to a Viking longship lost in a cold, dense fog for 3 days. The crew is on edge. Supplies are running low. Morale is sinking. They have no idea if they are heading towards the safety of Iceland or into the endless ice fields of the north. The chieftain, the ship's captain, is calm. He reaches into a leather pouch and pulls out a small, milky-looking crystal. He holds it up to the brightest part of the grey sky. He rotates it slowly, his eyes fixed on the light passing through it. He turns it back and forth, narrowing the angle. Then he stops. He points to the port side of the ship. "The sun is there," he says. "Steer this course." Hours later, the fog begins to thin and the faint, dark shape of a mountain peak appears on the horizon. Land, they are saved. The sunstone wasn't a primary navigation tool. It was their GPS for a cloudy day. It was a piece of secret technology, a sliver of geological genius that gave them a critical edge and allowed them to dominate the North Atlantic. It was a testament to their incredible powers of observation, their ability to see the hidden patterns in the world around them. But even the Vikings' incredible voyages pale in comparison to what was happening on the other side of the world. The challenges of the Atlantic were immense. It is a liquid continent, covering a third of the Earth's surface. Its distances are so vast they defy easy comprehension. And scattered across this immensity are thousands of tiny islands, many of them low, lying coral atolls barely visible from a few miles away. Finding one is like trying to find a single grain of sand on a football field blindfolded. And yet, it was populated. From Southeast Asia, a wave of humanity spread out across this ocean in outrigger canoes, performing the greatest feats of exploration in human history. We call them the Polynesians. For a long time, the prevailing academic theory, pushed by explorers like Thor Heyerdahl of Kon-Tiki fame, was that the Pacific was settled by accident, that ancient mariners were blown off course in storms. It is a view that robs them of their agency, their skill, their genius, and it is completely, demonstrably false. The Polynesians were not drifters. They were, without exaggeration, the greatest navigators the world has ever known. They were the astronauts of the canoe. Their voyages were deliberate, planned, and repeatable. They sailed from Fiji to Tahiti, from Tahiti to Hawaii, from Hawaii to New Zealand, and all the way to Easter Island, the most remote inhabited place on Earth. They did this against prevailing winds and currents, which proves their voyages were intentional. You don't accidentally sail 2,500 miles into the wind. How did they do it? Their technology wasn't in a crystal. It was in them. Their primary instrument was the human body tuned to the environment with a sensitivity that seems almost superhuman to us today. They practiced a holistic science, a system called wayfinding. It wasn't about one technique. It was about integrating dozens of streams of information from the world around them into a single, dynamic mental map. It began, as always, with the stars, but the Polynesians, they created what is known as a star compass. They knew the precise point on the horizon where specific stars would rise and where they would set. And they didn't just know one or two, they memorized the paths of hundreds of stars. Their mental compass wasn't a 4-point system of north, south, east, west. It was a 32-point compass, with each point defined by the rising or setting of a specific star or constellation. To sail from Tahiti to Hawaii, for example, a navigator would set his course by the rising of Arcturus. As the Earth turned and Arcturus climbed too high in the sky to be a reliable guide, he would switch to another star rising in the same direction, and then another and another, following a chain of stellar signposts across the ocean. At the same time, he was tracking his latitude. He did this by observing the height of stars. He knew that for his home island, a certain star would be a specific height above the sea at its zenith. This was often measured in a beautifully simple way by holding up his hand at arm's length. Maybe a particular star was one hand span high. To get back to that island, he just needed to sail north or south until that star was at the correct hand. Span height, once again, he was sailing along a line of latitude that he had etched into his memory. And that's where the true genius of the wayfinder becomes apparent. When the sky went dark, they learned to read the ocean itself. The surface of the ocean is not a random chaos of waves. It is an incredibly complex tapestry of patterns. The dominant pattern is the swell, the long, rolling, powerful waves generated by distant storms and trade winds. These swells can travel for thousands of miles. A master navigator, a Pelu, would spend his entire life learning to feel these swells. He could lie down in the bottom of his canoe and feel the rhythm of the ocean in his bones. He could distinguish between up to 5 different swells coming from different directions at the same time. There would be the primary swell from the east, a secondary swell from the northeast, perhaps another from a storm system hundreds of miles to the south. Each had a unique signature. By keeping his canoe at a constant angle to these swells, he could maintain a steady course for days on end, even in total darkness or cloud cover. He was steering by the pulse of the planet, and then came the most subtle and brilliant technique of all. He could use the swells to find land. An island, even a small one, is a physical barrier. As a deep ocean swell approaches an island, it is blocked, This creates a distortion, a kind of wave shadow that can be detected long before the island is visible. A navigator could feel this change. The canoe would begin to pitch and roll differently. He might feel a reflected swell, a wave pattern bouncing back from an island that was still 50 or 60 miles away, well over the horizon. He could feel the presence of land through the soles of his feet. This is a level. We live in a world that deafens our senses. They lived in a world where survival depended on hearing the whispers of the ocean. They had a whole vocabulary for these subtle wave patterns, and this was all stored in their memory. But there were still more clues. They were master naturalists. They knew the flight patterns of birds. A bird like the frigate bird might range 100 miles from land to fish, but it must return to its nest at night. Seeing a flock of them heading in a determined direction at dusk was as good as a signpost pointing to land. They watched the clouds. A stationary bank of clouds on a windy day often means there is an island beneath it, its peak causing moisture to condense. The color of the clouds could offer clues too. The underside of a cloud might reflect the pale green of a shallow lagoon, a signal invisible. They could see the deep phosphorescence of the water that indicated an upwelling of nutrients near an island's shore, to help teach and remember this vast body of knowledge. They created one of the most remarkable artifacts in the history of navigation, the stick chart. These are not maps in the way we understand them. You can't use one to get from A to B. They are abstract, mnemonic devices. Made from strips of palm rib, the sticks represent the direction of the dominant swells. Curved sticks show how those swells bend around islands, and the islands themselves are marked by small cowrie shells. A young apprentice navigator would study these charts for years, not as a map, but as a textbook. A way to visualize the invisible forces of the ocean until that mental model was so deeply ingrained he no longer needed the chart. It was a complete system, a symphony of observation, memory, and an intimate, profound connection to the natural world. It allowed them to perform the greatest migration in human history and to build a civilization across a liquid continent. And they did it all without a single piece of metal, without a single written word. Their legacy is a powerful reminder that technology is not always a physical object. As the Polynesian canoes were expertly crisscrossing the Pacific, a different kind of revolution was brewing back in Europe. The age of sail was giving way to the age of discovery. European powers, Portugal, Spain, England, were building bigger, stronger ships. Their ambitions were now global. They wanted to chart the entire world, to build empires, to control the trade routes to the riches of the East. The magnetic compass, an invention from China, had made finding north trivial, rain or shine, and their understanding of celestial navigation had become much more mathematical, much more precise. They had instruments the ancient Greeks could only dream of, the astrolabe, the quadrant, the cross staff. These devices allowed them to do one thing with incredible accuracy, determine their latitude, their north-south position. The height of the sun at noon, or the height of Polaris at night, changes in a predictable way as you travel north or south. At the equator, Polaris is on the horizon. At 0 degrees, at the North Pole, it's directly overhead, at 90 degrees. Every degree of latitude you travel north, Polaris gets 1 degree higher in the sky, so by measuring that angle you could know your latitude precisely. Columbus, Magellan, Vasco da Gama. They were all masters of this. They could sail west along a single line of latitude with confidence. Finding their latitude was the easy part. But there was another, far more difficult question. A question that would haunt sailors for the next 300 years. How far west have we gone? What is our longitude? This was the great unsolved problem of the age, the nightmare that kept... But longitude is a human invention. It is a problem of time. The Earth spins 360 degrees in 24 hours. That means every hour the Earth rotates 15 degrees. So if you know the local time where you are, and you simultaneously know the time at a fixed reference point, say London, the difference between those two times tells you your longitude. If your local time is noon, when the sun is at its highest point, and you know that you are at 45 degrees west longitude, it sounds so simple. But how, on a pitching, rolling wooden ship in the middle of the Atlantic? In the 17th century, do you know what time it is in London? It is an impossible question. Clocks in that era were based on pendulums. They were delicate, inaccurate instruments on land at sea. With the violent motion of the ship, the changes in temperature and humidity, They were and every second of error in time meant a huge error in your calculated position. An error of just 1 minute in time translates to a positional error of 15 nautical miles at the equator. This wasn't an academic puzzle. It was a matter of national security and economic survival. Ships laden with treasure from the New World would sail for weeks, thinking they were approaching the coast of Spain, only to smash. Naval fleets, the pride of their nations, would miscalculate their position and be lost to storms. The scale of the disaster was immense. The breaking point came on a foggy night in October of 1707. A fleet of British warships under the command of Sir Cloudesley Shovel was returning home after a campaign in the Mediterranean. They were sailing in treacherous waters near the Scilly Isles off the coast. Their navigators believed they were in safe open water. Far to the west of the islands, they were catastrophically wrong. 4 of the great warships, including the flagship HMS Association, ran aground on the rocks and were obliterated. Nearly 2,000 sailors, including Admiral Shovel himself, drowned. It was one of the worst maritime disasters in British history, and it was caused entirely by a failure to calculate longitude. In 1714, the British government passed the Longitude Act. It established a board of experts, the Board of Longitude, and offered a spectacular prize, the modern equivalent of millions of dollars, to anyone who could solve the problem of finding longitude at sea. It was one of the great scientific challenges of the century, and the greatest minds in the nation turned their attention to it. The scientific establishment, they proposed a complex method called lunar distances. The moon moves relatively quickly against the background of the stars. If you could create precise tables predicting the moon's position relative to certain stars for every hour of the day, as seen from London, a sailor could measure the moon's position, consult his tables, and calculate the time in London. It was a brilliant, elegant, celestial solution, but in practice, a tiny error in measuring the angle from a pitching ship's deck could lead to a massive error in position. And what if the moon or the key stars were obscured by clouds? The astronomers saw it as a problem of mathematics. But one man, an outsider, a man with no formal education, a man who the elite looked down on as a mere mechanic, saw it differently. His name was John Harrison, and he was a carpenter, and he believed the solution was not to look at the heavens, but to build a perfect machine. He believed it was possible to build a clock, a timepiece so accurate, so robust, that it could keep perfect London time on a ship, sailing for months through storms and calms, through tropical heat and Arctic cold. He proposed to build a